One of the things we're going to be looking at in terms of our thermochemistry is something called entropy. What entropy is a measure of the total amount of energy in a system. Now this energy comes from the position of the molecules, the energy in the bonds, the kinetic energy due to their movement. So it's all the potential energy and all the kinetic energy in a sample. This is really hard to measure. And so often what we do is rather than try and measure it directly, we measure it indirectly through change. And so what we would do is we would put the system under a chemical, physical, or nuclear change. We would measure the change in the entropy, and that would give us an idea of what it was before and after. So what we're going to do is we're going to look at our change in entropy. Now, because my entropy change is my final minus my initial, if I have less energy in my system after the change, it means I've given off energy to the surroundings, then my enthalpy change is going to be a negative value. And it's an exothermic system. If my final entropy of my system has more energy than my initial, then my entropy change is a positive value. And it's an endothermic system. Now, as we talked about in class and we did with our first activity, our entropy change can be measured through calorimetry. When we do calorimetry, we have different ways of doing it. A simple way that we can do it is we can just have a styrofoam cup. We could combine our two solutions and have our reaction take place in the solutions. And in this case, the styrofoam cup is my calorimeter. My system would be the chemicals or ions interacting, and my surrounding would be the water in which the chemical reaction takes place, because the water molecules would be surrounding the particles that interact. When we look at calorimetry, though, we're going to have three assumptions, and they're listed here. The first two assumptions basically state, or a way of stating, that all of the energy that my system gives off is going to go into the surrounding that I measure. And any that might be lost outside the calorimeter to the universe, or any that might be lost to the calorimeter itself, is negligible. And we're going to assume that all of the energy goes from my system of study to my surrounding that I measure. And then a final thing is, for dilute solutions, we're going to assume that they have the density and specific heat capacity of pure water. Now remember, a dilute solution is any solution with a concentration less than 1 mole per liter. Now, when we're looking at our entropy changes, one of the things that we have to keep in mind is our law of conservation of energy, which states that energy can be created or destroyed, only transferred from my system to my surrounding. So therefore, the absolute value of the energy change of my system is going to be equal to the absolute value of the energy change of my surroundings. So if my enthalpy change of my system occurs where I give off energy, then that will equal the energy gained by the surrounding. And so now we have our delta H is equal to plus or minus the energy change of our surroundings. Now, the reason we're saying plus or minus is because we're going to interpret. If you went and looked this up, it'd tell you it's equal to negative Q. That's because of how they calculate their temperature change. We're going to do two things. One, we're treating all temperature changes as absolute values. We're just looking at the absolute difference between my final temperature and my initial temperature. We don't care if it's increased or decreased. Two, we're going to always have a statement as to what my system is. So we're going to state if it's an exothermic system, then my enthalpy change will be equal to negative Q. And if it's an endothermic system, we will state that my delta H is equal to positive Q. Whenever we do a calculation or we're doing analysis, we are going to have to make one of these two statements depending on what my system is. The way we determine what our system is we can look at the information given about our system, or we can, more importantly, look at how my surrounding changes. And as if my surrounding has gained energy, then that means my system has given it off, and my system's exothermic. If my surrounding loses energy, that means that my system has gained it, and that means that it's an endothermic system. Now, when we look at our enthalpy changes, one of the ways that we commonly report it is in terms of molar enthalpy change, where it's just the enthalpy change for 1 mole of a substance that undergoes a change. Now, my molar enthalpy change is equal to my enthalpy change divided by my number of moles. Okay? Or my enthalpy change is equal to my number of moles times my molar enthalpy. And since my enthalpy change is equal to my plus or minus my Q of my surroundings, we get this equation. And this will be an equation that we will use for a number of examples and calculations from this point forward with calorimetry.